All right, we're ready to start Unit 4, which is all about polynomial functions and rational functions. We're not going to do a whole lot with rational functions, but what we're looking to do is be able to graph accurately higher order polynomial functions. And in order to do that, there's kind of a systematic approach, which we're going to break down into several different sections. Okay, so starting with section 4.1 today, we're going to look at the first couple of steps of being able to factor these higher order polynomials. And the first one is conducting the leading term test. This is going to tell us the end behavior of our graph, which is important so that when we're graphing it, we can check ourselves, right? And then we're also going to look at how to find the zeros, which we already know how to factor and find zeros, but specifically their multiplicities, because multiplicities are going to tell us whether or not the graph touches or crosses at those specific x-intercepts. Okay, so those are the two things we're going to look at in section 4.1, and then we'll look at the rest of the steps and actually putting it all together and graphing it in the next section in 4.2. Okay, so first we're going to look at the end behavior. End behavior is what is happening at the ends, right? So like think of a parabola. A parabola is either going to point up, so both ends go up, or it's going to point down, so both ends go down, right? Things like x to the first power is a straight line, right? Ends can go opposite directions, or even like an x cubed, right, is a little swooshy kind of shape where the ends go opposite directions. So we can actually determine that by just looking at the highest degree term, okay? Or in other words, the leading term. The leading term is the term that has the highest power or degree of x. And we're going to look at that degree and also the number part or the leading coefficient of that term, okay? So it's going to tell us what's happening as x goes to infinity and as x goes to negative infinity. Now in English, we just mean this is like in the right direction and in the left direction. So if in your homework it says, you know, determine the behavior as x goes to infinity, that just means what's happening out on the right side, right? If it says as x goes to negative infinity, that means we're looking in the left direction, okay? All right, so let's say we have some power of x, okay? Let's say x sub n. Okay, so a general form of a polynomial, if we have any polynomial, p of x, we write it as a sub n x to the n plus blah, 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 a whole bunch of stuff, a naught. Okay, so this is all the terms of our polynomial, okay? All the terms of our polynomial with this being our leading term, okay? When we look at that leading term, the leading coefficient, that's the number part. That's what we're calling a sub n, okay? And then the degree is this highest power of x, okay? So we're looking at those two things to determine what's happening at the ends. So we're going to use this little chart. Now this is something you're going to have to know. The chart's not going to be given to you with exams, okay? So this little chart says that if our degree, this little n, is even, so that would be something like an x squared or x to the 4th or x to the 16th or x to the 28th, right? If we have an even degree polynomial, then the ends go the same direction, okay? So that means they go the same direction, okay? If the degree is even, then notice both ends go up or both ends go down. If the highest power of x is odd, so if we have something like x cubed, x to the 7th, right? It's an odd number, then our ends go opposite directions, okay? Ends opposite direction, okay? Now, to determine which way they're going, okay, looking at just the power, we know if they're the same or if they're opposite, but we need to know if they're opposite, are they opposite like this or are they opposite like this, right? So that's where this leading coefficient comes in, that number part. If the number happens to be positive, okay, then notice what happens is the right side goes up, okay? Right, up. Okay, regardless if it's even or odd, if my leading number is positive, then it's going to open up to the right. So think about our parabolas we did, right? When we were talking about quadratic functions, if it had a positive leading coefficient, remember our parabola opened up. If we had a negative coefficient, then our parabola opened down. Same thing here, okay? And if our leading coefficient is negative, right, then notice the right side goes down. Right down. Okay, so we look at the degree to determine if the ends are the same or opposite, and then we look at the number part to determine what the right side's doing. And if we know what the right side's doing, we should be able to figure out what the left is based on if they're doing the same or if they're doing opposite. So let's look at some examples. So here, first we have to identify what is the leading term, right? So in this one, it's negative x to the fourth. That's the highest power of x in a term that we see. So negative x to the fourth. My degree is 4, right? And 4 is even. So if I have an even degree, that means my ends go the same direction. So I'm going to go ahead and say ends are the same, right? And if they're the same, now we have to figure out, are they both going up or are they both going down? So I look at my leading coefficient, which here, if it's just a negative, that's like a -1, right? So it's negative. So that means that the right side is going to be going down, okay? And then we want to sketch just a little picture. So if the right side's going down and the ends are the same, that means that the left side has to also be going down, right? We don't know what's happening in the middle. So it looks something like this, okay? Let's get another one. On this one, we look for our highest power of x, which is our leading term here. Now, it's not always our leading term. They don't always write it in a nice, pretty order for us. So our leading term in this case is 1/2 x to the 9th. The x power or exponent here is a 9, so that's our degree. This is a degree 9 polynomial, which is odd, which means that our ends are going to go opposite directions, okay? So ends opposite. Now we need to determine what the right side's doing. So the right end, we can determine if it's going up or down based on the leading coefficient. Here we have a positive 1/2 is our leading coefficient. So that means the right side's going up. So right side's going up, left side's going down because they're opposite, and we don't really know what's going on in between. So we're just going to make a little squiggle there. Okay. And then let's look at one more. We have 1 minus negative x plus 3x to the 10th. So the highest power of x in this case is that last term, right? 3x to the 10th. So this is a degree 10 polynomial, which is even. So we know that our ends are going to be going the same direction. And then we have to determine what the right side's doing based on that leading coefficient. Our leading coefficient in this case is positive. So that means that the right side is going up. Right side's going up and the ends are going the same direction means that the left side is also going up. We don't really know what's happening in the middle, right? All right, so that's really the gist of it. There's 3 for y'all to try on the next page, just being able to determine that end behavior. And I will tell you this, we do have a worksheet that goes with this section, and on the worksheet, the very first step that you're going to do is determine the end behavior. And this is what I'm looking for. I'm looking that you identify the leading term. I'm looking that you wrote ends same or ends opposite, and that you told me what the right side's doing, and that you sketch a little picture, because we're going to use that to check our final answer. So make sure that you are okay, fully understanding of how to do this, because it will be required on your worksheet. Okay. All right. Go ahead and try the ones at the top of page 3, and then we'll go over them in just a minute. Okay, so looking at the first one, our leading term is our negative 5x cubed. The x cubed tells us it's a degree 3, which means that our ends go opposite directions. And the negative 5 out front tells us that the right side goes down. So right side goes down, left side goes up. Okay. On our middle example here, our leading term is actually the one at the end of the polynomial, which is 1/3 x to the 7th. So that means it's a degree 7. So our ends go opposite, and because our leading term is positive, that means the right side goes up. Right side goes up. Ends are opposite, means left side goes down. Okay. And then on our last one, our leading term is actually the one leading, right, in front. And we have 6x to the fourth. So this is a degree 4 polynomial. 4 is even, which means our ends go the same direction. And because our 6 out front is positive, that means it's going to be going up on the right. Now, if it's up on the right, that means it's also up on the left, right? Okay, so now that we know how to determine that end behavior, now we want to move on to our next step of graphing these higher order polynomials, which is to identify the zeros and their multiplicity. So before we get into that, I just kind of want to refresh you on what zeros of a polynomial are. Okay, the zeros of functions or polynomial functions are the solutions we get when we set it equal to 0 and solve. Okay, so we refer to things as zeros because if we plug them into a function, they equal 0, right? Now, that doesn't necessarily mean that they are x-intercepts. They're only x-intercepts if they are real numbers, okay? In order to be an x-intercept, it has to be a real number. Because sometimes when we set a function equal to 0 and solve, we end up with answers that have like i's in them, right? And i's are imaginary. They're not things we could graph on an x-axis. So only the real number solutions end up being x-intercepts. Okay, so I want to refresh you on just how to plug something in to determine if it is a 0, right? We just need to see if it equals 0. And then we'll get into determining the behavior at those zeros. Okay, so to determine if a number is a solution, all we have to do is plug it in and see if it equals 0. If yes, then yes, it's a 0, it's a solution. If not, then it's not a 0 and it's not a solution. Okay, so let's look at this example. It says, consider p of x is equal to x cubed plus 2x squared minus 5x minus 6. And we want to determine if the numbers 2 and -5, if either of them are a 0 of this polynomial. So to determine if they're a 0, all we're going to do is plug it in. So we plug 2 into our function. Our function says to do our input cubed plus 2 times our input squared minus 5 times our input minus 6. So we're just plugging in a 2 everywhere we see an x in the original and simplifying. 2 cubed is 8. On my next term, 2 to the second power is 4 times the 2 out front gives us another 8. -5 times 2 is -10. And then we have that -6. So as I start combining, 8 and 8 gives me 16. And then you can see over here we have a -10 and -6. That's -16. So I end up in 0. So since it equals 0 when we plugged in 2, then that means yes, x equals 2 is a 0. Okay, whatever number we plugged in. All right, let's look at the next one. P evaluated at -5 means we're plugging in a -5 everywhere we see an x in our original. So we have -5 cubed plus 2 times -5 squared minus 5 times -5 minus 6. And then we're just simplifying. -5 cubed gives me -125. And then on the next term, we do our exponents first. So -5 squared is +25 times 2 gives me a +50. And then -5 times -5 is a +25, and then minus 6. So -125 plus 50 gives me -75 plus 25 minus 6. -75 and 25 gives me a -50 minus 6, so we're ending up with -56. So because it does not equal 0, then that means the number that we plugged in is not a 0, right? It's not going to be an x-intercept. So this tells us that x equals -5 is not a 0. Okay. All right, so I want y'all to try the same exact principle here. Okay, you're checking the same numbers, 2 and -5, but you're plugging it into this polynomial. So different polynomial, same process. So go ahead and take just a minute to do that, and then we'll go over them. All right, let's see how you did. On the first one, when you plug in 2, you should end up with -7, which does not equal 0. So that means that x equals 2 is not a 0 of this polynomial. Okay. When you plug in -5, however, it does simplify to 0. And so x equals -5 is a 0 of this polynomial. Okay. So that's how we can check to see if something is or isn't a 0. We can just plug it in and see if it equals 0. But if they don't give us the number to begin with, then they're expecting us to solve for the actual zeros. Okay, so let's, oops, I'm on the wrong page here. So now let's look at how to find the zeros. If one's not just given, sometimes they'll just give them to us and say, see if this is a 0, and we plug it in. But if it's not given to us, then we actually have to find the zeros of the function by factoring, right? So to find the zeros, we set the function equal to 0 and solve. So notice on this one, it's actually already factored for us. So all we have to do is set it equal to 0. So we do negative x minus 1, and I'm actually going to write this, since there's 2 copies of that, I'm going to write this as squared, times, notice we have 3 copies of the next one, so I'm going to write this as x plus 2 cubed, and I'm just going to set it equal to 0 because we're solving for the zeros. Now, these exponents do not tell me anything about my zeros, right? If I were to have not written it like this and set each one of these equal to 0, I would have to solve this one, and then I have to solve the same one again, and then I would solve x plus 2 equals 0, and then I would have to solve it 2 more times, but it's going to give me the same answer. So what these squareds and cubes tell me is that I have multiple copies of whatever solution I'm going to get from this factor. So when I set these equal to 0 and solve, I don't actually have to take that power with me, because that just tells me that I have multiple copies of that same 0 that I'm going to get. So I'm just going to go ahead and set this equal to 0, and when I solve it, I get x equals 1, and then I'm going to set this one equal to 0, and when I solve it, I'm going to get x equals -2. Okay, notice I didn't set this negative equal to 0 because it's just a number. There's no x there. If there's not a variable out there with your greatest common factor, it's not going to produce a solution for you. Okay, so we don't have to worry about that. So that means that the zeros that we got for this one is just -2 and 1. Okay. All right, let's look at the next one. Same thing on the next one, except it's not factored for us. So if it's not factored for us, then we have to factor it. So I'm going to go ahead and just write my function, set it equal to 0 so we can solve. And because I have 4 terms, I'm going to go straight into my grouping. Make sure you check for a greatest common factor before you start factoring. In this case, we don't have one, so we're going to go ahead and just go straight into our grouping method. So out of the first pairing, we can take out an x squared. And that leaves us with an x minus 2 when we factor out that x squared. And then out of the second pairing, I can take out a -9. When I factor out -9, that's going to leave me with an x minus 2. Still equal to 0. Okay. And now they both have that x minus 2 factor, so I take that out, which leaves me with x squared minus 9. And then from here I can go ahead and solve, but I actually want to factor it as far as I possibly can until my factoring methods no longer work. This one doesn't factor any further because it's an x to the first power, but this one I can factor further, right? Because it's an x squared, and this is a 9. Those are both perfect squares, and it's a subtraction. So I know that this is a difference of squares, right? And the bases that I'm squaring is an x for this one, right? And a 3 for that one. So I know that this is going to factor into x plus 3 times x minus 3. And that's going to be equal to 0. And then just like I did once I had this one up here completely factored, now I just set each factor equal to 0 and solve. So if I set this one equal to 0, x minus 2 equals 0, that gives me x equals positive 2. When I set x plus 3 equal to 0, that's going to give me a -3 for my 0 when I solve it. And then x minus 3 equal to 0 is going to give me a positive 3 when I solve it. Okay, so that means that the zeros of this function are -3, 2, and 3. I always like to list them in order from smallest to largest. My math lab shouldn't count you wrong if you don't have them in that order, but it's just a good habit to get into. Okay? All right, let's look at one more. This one has 3 terms, so I'm already just thinking some product chart, but it has an x to the 4th and an x squared, right? So that's not what we're used to seeing. We're used to seeing an x squared and then an x. So I'm going to do substitution because I'd really like this middle term to be a variable to the first power. I would really like this to be something like 4m, right? Not 4x squared. So I'm just going to go ahead and let m equal x squared so that I have just a variable to the first power there. Okay? That would make this leading term an m squared. And now this looks like something that I can use my sum product chart for, right? So if I do my sum product chart, my sum is going to be my middle coefficient, which is a 4. My product is going to be my first coefficient times my last, so -45. So I need something that multiplies to -45 that I can combine to get 4, which would be a +9 and a -5. And I can use my shortcut, right? Because my leading coefficient is a 1. So that tells me this is going to factor into m plus 9 times m minus 5. And then I'm going to go ahead and set each of these equal to 0 and solve. So m plus 9 equals 0, which gives me m equals -9. And on this one, m minus 5 equals 0. So that means that m equals 5. So we've solved and got our answers, but we've solved for m. Okay, so now that we've solved for n, we need to plug these back in. Plug back in for m. Okay, so we know that m equals -9 or m equals 5, and m was originally x squared. So really this means that x squared equals -9 or x squared equals 5, right? And now I can finish solving for x. So I can do the square root. So I get x is equal to plus or minus the square root of -9, or x is equal to plus or minus the square root of 5. Now the square root of 5 does not simplify, so I'm just going to leave it like that. This one, though, I can simplify because that negative can come out as an I, right? And then the square root of 9 is a perfect square. So we get x is equal to plus or minus 3i, or plus or minus the square root of 5, which means that our zeros, when we write them in my math lab, would be -3i, positive 3i, negative square root of 5, and positive square root of 5. Okay. All right, so now we know how to find our zeros. That was just a quick little refresh on basically what we did in Unit 3, right? We know how to factor and solve, and how to use substitution with factoring to solve. So now that we have our zeros, now we're going to look at the behavior at them. So notice on these first two, we ended up with real number zeros. So these are actually going to be our x-intercepts. That means this one's going to touch or cross at -2 and 1. This one's either going to touch or cross the x-axis at -3, 2, and 3. But on the last one, I ended up with 2 complex answers. So while these are zeros, these are solutions, they're not going to be x-intercepts, right? Only the real number solutions are going to give us actual x-intercepts that we can graph and determine if they touch or cross, okay? All right, so to determine if they touch or cross, we're going to look at their multiplicity. Multiplicity is the number of occurrences of the zeros in the function. And we can look at that in its factored form. So when we get the function completely factored to where we have all these little factors that look like this, all we have to do is look at how many copies of that factor do we have, right? Before we set it equal to 0 and solve each little factor, we want to know how many copies we have. If the number of copies, or the little exponent on our factor, if the number of copies is odd, then we know that the graph is going to crosses the x-axis at that given intercept. Okay? If the little exponent or the little number of copies we have of that factor is even, then we know it touches the x-axis at that given x-intercept. Okay? So what I want to do is I want to look at the same exact 3 examples we just did on the last page. Notice these are the same ones. And we're going to list them out in factored form so that we can determine if it touches or crosses at each of the zeros. Okay? So you can refer back to this page where we just worked these out. I'm going to go ahead and just copy it over. So g of x, we said we could write this as negative x minus 1 squared times x plus 2 cubed, right? We knew that this one produced the x equals 1, 0. So now we want to identify what the multiplicity is. So the multiplicity here is how many copies of that factor that we got the 0 from do we have? Here we have 2, so this is multiplicity 2, which is an even number, so that means it's only going to touch at that x-intercept. So this touches, and we want to write what the x-intercept is. We don't want to just leave it as x equals 1. As an x-intercept, that would be 1, 0. Okay, so that's everything we need to know about that 0. Now I want to do the same thing with this one. Okay, when we solved this, we got x equals negative 2. Now we want to see what the multiplicity is. The multiplicity is the number of copies we had of the factor that 0 came from, or how many copies of that 0 are we going to get. In this case, it's 3. Multiplicity 3 is odd, which means it crosses. So this is going to cross at the x-intercept, negative 2, 0. Okay? So that's all we're doing, just determining if it's touching or crossing based on how many copies we have of it. So let's go ahead and write in what we got for this one. When we fully factored this, it ended up being x minus 2 times x plus 3 times x minus 3. And when we solved them, this factor gave us a positive 2, this factor gave us a negative 3, and this factor gave us a positive 3. And notice, if you look at each of these little factored quantities, I don't have more than one multiplicity, right? It's like I have one copy of each of these factors. So all of these are multiplicity 1, right? And multiplicity 1 is odd, so that means it's going to cross at all of these x-intercepts. And so I just need to write them as x-intercepts. So this is going to be 2, 0, this one's going to be negative 3, 0, and this one's going to be 3, 0. Okay? If they're all the same, I'm fine with you writing it like this and just kind of drawing a line, but I want to make sure you know to identify all of that. Okay? Let's look at our very last one. Now this one was a little tricky because we didn't actually factor it, we just found all the solutions, right? But we can take any solution and write it back in factored form. And what I mean by that is, look at this last one we did. We ended up with x equals positive 2, and in factored form, it's x minus 2. So it's almost like we'd be taking this 2 and moving it back across to figure out what the factor is. If I move the 2 back across, I get x minus 2, right? If I take this negative 3 back across, I end up with x plus 3. If I take the positive 3 back across, I end up with x minus 3. So if I know what the solutions are, I can just move them back across to figure out what the factor was. So I'm going to go ahead and write what zeros I got. I got negative 3i, positive 3i, negative square root of 5, and square root of 5. Okay? So if I wanted to write this in factored form, just think about moving those zeros back across. If I move this one back across, I'd get x plus 3i. If I move the next one back across, it would be x minus 3i. If I move negative square root of 5 back across, it would be x plus the square root of 5. And the last one, positive square root of 5, if I move it back across, we would have x minus the square root of 5. Okay? All right. So we have it in factored form. We know what our zeros are, so we just need to identify our zeros, our multiplicity, if they touch or cross at the x-intercept. Now these two, we got x equals negative 3i, and we got x equals positive 3i. These are complex numbers. They're imaginary, right? So if these are imaginary numbers, that means we cannot graph them. So they are solutions, but we're not going to state whether it touches or crosses and try to write them as x-intercepts because we can't graph them. They're not x-intercepts, right? But these two we should be able to do. So this one was the 0, x equals negative square root of 5, and this one was the 0, x equals positive square root of 5. Notice the multiplicity on both, because both factors we only had one copy of, right? So both of these have multiplicity 1. 1 is odd, so that means it's going to cross at these x-intercepts. Okay, both have multiplicity 1, both cross. I just need to write it as an x-intercept. So negative square root of 5, 0, and square root of 5, 0. So there's all the information that I need on these two zeros. Okay? All right. So on the next page, there are 3 for y'all to try, okay? Doing the same thing. I want you to start by factoring and solving, right? This one's already factored for you, so you just have to solve it. Determine the multiplicity of each 0, whether it touches or crosses, and then write that x-intercept, if it happens to be a real number, as a ordered pair. Okay, so there's 3 for y'all to try. Go ahead and pause the video, and then when you're ready, we'll check you, see how you did. All right, so on the first one, it's already factored, but I went ahead and wrote it so I could see how many copies there are. There's 3 copies of the x minus 1 factor. There's only 1 copy of the x squared plus 4 factor, and there's 2 copies of the x plus 6 factor. Now the 5, I don't have to set it equal to 0, right? Because it doesn't have a variable. So this is actually just going to be a vertical stretch of the graph, not actually something that's going to produce a 0. But when I set x minus 1 equal to 0, I get a positive 1. It came from a cubed factor, so its multiplicity is 3, which means it crosses at that x-intercept, which would be 1, 0. Okay? The middle one is not fully factored, right? Because this is not a difference of squares, and it's not a sum or difference of cubes. So we just set it equal to 0. When I move my 4 over, it becomes negative. And then when I take the square root of both sides, I'm going to get plus or minus 2i. Now this is a complex number, so even though plus or minus 2i does give us solutions, it does not give us x-intercept. So we cannot graph it, so we're just going to circle that as a solution, but not as an x-intercept. Okay, we move on to the next one. When I set x plus 6 equal to 0, I'm going to get x equals negative 6. It came from a squared factor, so that's going to be multiplicity 2, which means it only touches at the x-intercept 6, 0. Okay, let's look at the next one. The next one was one you had to factor, and we factored it using grouping. So out of the first pair, you should be able to take out an x squared. Out of the second pair, a negative 1. So we end up with x plus 3 times x squared minus 1, and then this is a difference of squares. Now, if you solved it by using the square root, if you just said x squared minus 1 equal to 0, that's fine, but make sure that you know the multiplicity of each 0, right, and that you didn't forget your plus or minus. If you factor it as a difference of squares, it should factor into x plus 1 and x minus 1, and then we set each of these factors equal to 0. So the plus 3 is going to give us a negative 3 solution, the plus 1 gives us a negative 1 solution, and the x minus 1 gives us a positive 1 solution. I have 1 copy of all of these quantities, which means they're all multiplicity 1, which means that it's going to cross at all 3 x-intercepts. So make sure you write them as ordered pairs. Okay? And then the last one was one we had to use substitution on. So I went ahead and let m equal x squared so that I could do the sum product chart, which gives me m minus 3 and m minus 3 and minus 1. So when I solve it, I get m equals 3 or m equals 1. But remember, we're not solving for m, we're solving for x squared. So at this point, I have to put back in what m was. M was x squared, so that means x squared equals 3, or x squared equals 1. And then we solve by taking the square root of both. Square root of 3 doesn't simplify. Plus or minus the square root of 1 just gives me plus or minus 1. And notice, I know that multiplicity is 1 on all of them, and the reason I know that is because this is a degree 4 polynomial. So when I get this all factored out, how many zeros I could have potentially, the most possible zeros I could have with an x to the 4th is 4 zeros, right? If I have less than 4, say I have 3, then that means one of these I must have an extra copy of, right? But since I ended up with 4, the only way that, it's not possible that they have more than one copy. Because if I take this factor times this factor times this factor times this factor, I end up with an x to the 4th. So that means I just have one copy of all these zeros, which means it crosses at all of their intercepts. And because they're not complex, they're real numbers, I can go ahead and write them as x-intercepts, okay? All right, so just to give you a little visual of what we have determined so far, we have determined the end behavior, okay? End behavior is based on the leading term, the a sub n x to the n. So let's pretend maybe it's an odd degree. So maybe we know this side's going up and this side's going down, okay? Then we find the location of the x-intercepts. That's just solving, right? Set equal to 0 and solve. That tells us where all of our solutions are. So maybe we have one here, 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 and here, right? Maybe those are our x-intercepts. Then we determine our behavior. So this is where we look at the multiplicity to determine if it touches or crosses, right? So maybe we determine that maybe this one crosses, maybe this one crosses, maybe this one crosses, and maybe this one touches, right? So we should be able to kind of draw a little bit of a graph here. I know that this is going to come down and cross, and I don't know how far it's going to come down, but this is going to come back up and cross. And I don't know how far up it's going to go, but then it's going to have to come back down and cross. And then up here it's going to come up, but this one's a touch. So it's not going to cross, it's just going to touch and then go back down the same direction. So from what we learned today, just knowing the end behavior and the location of the x-intercepts and the behavior at those intercepts, we should kind of have a pretty decent shape. What we're going to look at in the next section is now to make our shape look a little bit more accurate. We're going to look at finding our y-intercept. So if we figure out our y-intercept is way up here, right, that's going to help us make a better shape because we're going to know this loop comes a little bit higher than we had initially drawn it, right? And we're also going to pick some test points in between all of our zeros, right? Because if we pick a test point here and we get a positive number, we know we did something wrong, right? Because if we plug in a test point, we should get a negative value down here that helps us graph it, right? If we pick a test point between these two zeros, it may be way down here. And so that's going to help us to draw a better picture. Okay, same thing, we may plug in a test point and figure out that it's way up here, and maybe our loop doesn't go down so low. Okay, so the test points and the y-intercept we're going to go over in the next section, and then we'll have enough information to go ahead and graph it with a good picture. But I do want to show you two more problems of like potential word problems that you're going to see in this section. Okay, now both of these solving techniques you've done before. It's more of just I want you to read through the problem and be able to identify what it is they want us to do. Do they want us to set this function equal to a value? Do they want us to plug into the function? Are they wanting us to find vertex? So let's go ahead and look at those. This one's talking about print book sales. It says the sales of print books increased about 7% from 2012 to 2014. The sales data over the years 2008 to 2014 are modeled by this cubic function, okay, where x is the number of years after 2008. Okay, and S of x is the number of print books in millions. So they're telling us what this function represents. They're saying we're plugging in the number of years after 2008, and it's telling us the number of books in millions. Okay, all right, so now that we know what it represents, let's see what it's asking us. It says find the number of print books sold in 2009 in 2014, and in 2015. So we're looking at for 3 different answers. I'm going to just look at the first one, okay? 2009. Okay, we want to find the number of print books. So we're looking for the function value. We're looking for the y, right? So if we're looking for the y, then that means we should know the x. The x is years, right? It tells us x is the number of years after 2008. So we're not actually taking 2009 and plugging it into the function. We first have to identify how many years have passed in 2009 since 2008. Right? So from 2008 to 2009, 1 year has passed. So that means our x value is 1. Okay? And we could do that for both of these. We could figure out that the x value of 2014, how many years from 2014 since 2008, that would be 6, right? And the same thing with 2015. That would be x equals 7, because 15 is 7 years after 2008. Okay. So on this one, it's just a basic evaluate the function where we're just plugging in a number to see what the answer is, but we're not plugging in the given value. We have to take that given value, that given year, and figure out what value to plug in. Okay. So for 2009, oops, pretend there's another 0 in there. That's horrible. Here we go. 2009, we know x equals 1 because it's 1 year since 2008. So if we plug in a 1 for x, so we're doing s evaluated at 1. So when I plug a 1 into this function, I get 4.958 times 1 cubed minus 38.125 times 1 squared plus 26.417 times 1 plus 778. And now this is something we should be able to simplify on our calculator, right? I'm going to go ahead and just tell you what it equals because I believe in my heart that y'all can do this simplification, okay? So when I simplify all these numbers, this comes out to 771.25. And remember, we were plugging in x equals 1 for the year, right? Because we're given the year and we're trying to figure out the number of books. So once we get our answer, this is not 771 books. This is 771 million books, right? Because S of X represents the number of print books in millions. And I'm going to go ahead and just round it. We're going to say this is about 771 million books for 2009. Okay, and then we would do the same thing for 2014 and 2015. So 2014, we would plug in x equals 6, and then 2015, we would plug in x equals 7 and simplify. Okay, I'm not actually going to work those out because I believe that you know how to plug in a number in there to get your solution. Okay, instead, I want to show you this last problem, which is projectile motion. This says a stone is thrown downward with an initial velocity of 34.3 meters per second, will travel a distance of s meters. A distance of s meters is what this function's talking about. Okay, so this is my distance that the rock is traveling, right? And it says it's modeled by the function below where t is in seconds. Okay, so this is telling us the distance for a certain number of seconds. So we have seconds going in and the distance traveled as our output. Okay, it says if a stone is thrown downward at this rate from a height of 294 meters, how long will it take the stone to hit the ground? Now the fact that it's asking how long, that means we are solving for seconds. Okay, we need to know how long. We're looking for t. Okay, now if we are looking for t, we should know the distance. They're not going to give us a problem where we don't know one or the other. So if they want us to find distance, they're going to give us the seconds to plug in. If they want us to find the seconds, they're going to give us the distance to set it equal to. So here what we're looking for is the distance that this rock has traveled. So it says if a stone is thrown at this rate from a height of 294 meters, how long will it take the stone to hit the ground? So if I'm throwing it from up here at 294, dropping it from 294 294 meters, and it goes all the way down and hits the ground, it has traveled a distance of 294 meters. So that is my distance, 294, and I just set that equal to my function. Okay. Now, in order to solve this, I see a t squared. That tells me I'm going to have to factor or do quadratic formula, so I need it equal to 0. So I have 0 is equal to 4.9 t squared plus 34.3 t minus 294, right? Because I got to take that 294 and move it to the other side. And then I really don't want to do sum product with this. I'd much rather do quadratic formula because there's decimals. So our quadratic formula says to do negative b, or the opposite of my b, negative 34.3, plus or minus the square root of my b squared, so negative 34.3 squared, minus 4 times my a, which is 4.9, times my c, which is negative 294, all over 2 times my a, which is 4.9. Okay, so the only new thing in here is, well, really, there's really no new thing. It's just reading through the problem and making sure you can set up the equation, and then your solving method is something we've already been over before. Okay, again, I'm not going to work this out. I believe y'all can simplify a quadratic formula problem. I will tell you that it equals 5 and negative 12 are the two answers we get when we finish doing our quadratic formula. Now, because we are solving for seconds, we're trying to figure out how much time has passed with this rock being thrown down and hitting the ground. So we can't have negative time, right? So that means it would take 5 seconds. If you want to work this out and make sure you get these two answers, by all means, please do so. But I'm not going to take time in the video to work that out because that's something we've already covered. Okay, all right, so that is the end of section 4.1. You should now be able to complete that assignment. If you have any questions, please let me know.